Good morning and welcome to NutriQuest, a healthy eating adventure game we built for children aged 8 to 12. My name is Jason, and today my team and I will show you how we combine game design with educational value to solve a real-world problem. The problem we're solving is straightforward but serious. Children in the 8 to 12 age group are increasingly making poor food choices containing high sugar and junk food with low nutrition. Statistics back this up, showing 1 in 5 children being overweight and 70% regularly consuming processed food. This age window is particularly critical as habits formed here persist into adulthood. So, the question we asked ourselves is, how do we actually change this? So, why do we actually build a game? Traditional approaches like pamphlets, classroom lessons, food pyramids all have one fatal flaw, which is that kids do not engage with them. Research consistently shows that game-based learning dramatically improves retention. In NutriQuest, every mechanic reinforces nutrition concepts like collecting healthy points earns points, junk food costs health points, and wrong answers have real in-game consequences. The learning is baked into gameplay, which is why we chose this medium, and it directly fulfills these brief requirements to apply our abstract engine to a real-world problem and something meaningful.
So now that you know what NutriQuest is trying to solve, let me show you how we actually built it, because the architecture is really the heart of the project. Our code base is split into two distinct layers. The engine layer, completely abstract, zero game logic, no mention of food, nutrition, or scores anywhere. The simulation layer, this is NutriQuest. It extends the engine-based classes and plugs in all game-specific behavior. Think of the engine like a blank film studio. Lights, camera, a stage and director. The simulation is the actual movie being shot. The studio doesn't know or care what the movie is about. The entry point is a class called Game Master. It owns 6 specialized managers and runs the game's loop in order every frame. Time Manager, Input, Scene Manager, Entity Manager, Movement Manager, Collision Manager, Render, and Repeat. The first major system is Scene Management, which implements the state pattern. Every scene, the menu, the 3 levels, and the end screen extend an abstract scene class with 4 required methods: start, stop, update, and render. The Scene Manager simply holds the current scene. When switching levels, it stops one scene and starts the next, while the game loop just calls update and render on whatever is active. That's polymorphism in action. The second system is the Entity Model. Every object in the game, the player, and all food item is an entity. The Entity Manager looks through all active entities and updates and renders them without needing to know their specific type. This again uses polymorphism through a shared base class. To ensure safety, we use a pending changes queue, so entities aren't added or removed mid-loop, preventing concurrent modification exception. Next is the strategy pattern for food movement. We created a movement strategy interface with 3 implementation: float strategy for slow drifting food, circle strategy for orbiting food using trigonometry, and dash strategy for junk food that bursts in random direction. Each food item holds a movement strategy and simply calls strategy.update. Changing movement only requires swapping the strategy object. The food class never changes. Finally, collision detection uses AABB bounding boxes. Every active entity pair is checked each frame. The collision manager then looks up the correct response using a hash map of listeners' callback keyed by layer pairs. For example, player with good food triggers a score handler. Detection and response stay fully decoupled, demonstrating the observer pattern. So the whole architecture comes down to one idea: a fully abstract engine underneath, NutriQuest on top, connected through interfaces and design patterns. Over to Wei Long for the engine improvements.
Now I'll be talking about the engine improvements. We've updated the game engine to make it cleaner and easier to expand. Here are the 6 main changes we did to the code. Firstly, the strategy pattern. We separated how things move and work. For example, freeze or shield power-ups are now separated from the main engine. This let us add new abilities without changing the core codes. Secondly is template method pattern. We made a master template for game levels. Instead of writing hundreds of lines for every new stage like the kitchen or jungle, we only need about 20 lines to set up now. Third is factory pattern. We created a single food factory. If we want to add a new food item, we just add 1 line to the factory instead of searching through the whole project. Fourth is SRP extraction. We separated the brain of the game from the eyes. The game state handles the score and health, while the renderer only handles drawing. They don't get in each other's way anymore. Fifth is level config objects. We moved all the settings, like how fast the game goes, into one place. There are no more random numbers hidden in the code. We just changed one file to balance a level. Lastly is Java 2D visuals. We moved from basic shapes to real PNG images. We added a catch to make loading fast, along with health bars, animated characters, and floating text for points. These steps make the game faster to build and much easier to fix.
Let me walk you through the 6 design patterns used in this codebase and why they matter. First, the strategy pattern appears in 2 places. In the main game, power-ups like freeze, shield, and double points each encapsulates their own behavior, so the game loop just calls a single method without knowing the details. In NutriQuest, movement behaviors like floating, circling, and dashing are also separated into strategies. The key idea here is flexibility. We can add new behaviors without changing the existing code. Next is the template method pattern. Used across both hierarchies, a base class defines overall flow like starting, updating, and stopping a level, while subclasses only provide specific configurations. This keeps shared logic in one place and makes each level extremely lightweight. Third, the factory pattern is handled by a food factory. All food objects are created in one central method, which decides their type, point, speed, and movement strategy. This completely decouples the object creation from the rest of the system. Fourth, the observer pattern is used for event handling. The engine detects collisions and notifies listeners, while the system, like scoring and quizzing, react independently. This keeps the game engine and logic loosely coupled. Fifth, the facade pattern is implemented through Game Master. It hides the complexity of initializing and wiring multiple managers, giving the game a single entry point to the engine. Finally, the manager pattern instructs the engine into 6 focus subsystems, each responsible for one thing, like scenes, entities, or output. This separation is what made it possible to build the entire NutriQuest game without modifying the engine at all. Overall, these patterns work together to keep the system modular and extend.
For our system design, we applied the solid principles to ensure the architecture is clean, flexible, and easy to maintain. First, single responsibility. Each class has one clear role. For example, the nutrition tracker only handles score and health, while the quiz manager is responsible only for quiz logic. This keeps our code simple and easier to debug. Next, open-close principle. Our system is open for extension but closed for modification. We can add new food types through the food factory, introduce new levels by extending level scene, and add new movement behaviors using movement strategy, all without changing existing code. For list of substitution, our subclasses like market scene, kitchen scene, and jungle scene can all be used wherever a level scene is expected. Each scene follows the same structure, so the system behaves consistently. Then, interface segregation. We use small focused interfaces such as iMovable, iCollision Listener, and movement strategy. This ensures classes only depend on what they actually need. Finally, dependency inversion. High-level components depend on abstractions instead of concrete implementations. For instance, food depends on the movement strategy interface, allowing us to change behaviors without modifying the food class. Overall, applying these principles results in a modular, extensible, and maintainable game architecture.
Food entities in our game are divided into 2 main categories, healthy and junk foods. Healthy foods like apples, bananas, and vegetables add to the player's score and increases their health points. In contrast, junk foods such as burgers and sodas reduce the player's health points, making the game more challenging. Movement is driven entirely using strategy pattern. For example, the flow strategy gives healthy food a gentle random drift, making them easier to collect. Circle strategy creates orbital movement, which requires better timing from the player, and on the other hand, dash strategy is used for junk food. It creates a fast, aggressive burst of movement, which helps communicate danger through motion. Overall, this creates a clear difference between safe and dangerous objects, both visually and behaviorally. Next, I'll explain more about our power-up feature. So our power-ups acts as a reward system that helps the players recover or gain an advantage as the game gets more difficult. When players reach certain score milestones, they can choose one of the 3 power-ups. The first is double points. For a short period, the players earn more points when collecting healthy food. The second is shield. This blocks the next hit from the junk food, and then it disappears after it's being used. Third is freeze. This temporarily stops the movement of junk food, giving the players a short window to recover. Overall, these power-ups add more variety to the gameplay and gives the player more control in difficult situations. Another key feature of our game is the quiz system. The quiz is triggered when the player eats an unhealthy food. The game then pauses briefly to display a multi-choice question related to nutrition. If the player answers correctly, they're rewarded with extra time, which can help them continue in the level. If they answer incorrectly, they will lose additional health points and increasing the challenge of the game. The questions are randomized each round to keep the game fresh. In terms of level progression, the game is divided into 3 stages, breakfast, lunch, and dinner. Each level introduces a different food combination and a slightly higher difficulty, making the game progressively more challenging while still keeping it easy to understand. Our game focuses on 4 main ideas. First, behavior-driven difficulty. Junk food moves faster and more unpredictably than healthy food, so the movement itself shows what is safe and what is not. Second, education is built directly into the gameplay. The quizzes cannot be skipped, and correct answers extends the player's time, so learning is naturally rewarded. Third, the game uses meal-based progression, breakfast, lunch, and dinner, which makes the content more relatable to real-life eating habits. And finally, we built all of this without modifying any engine classes. This shows a clear separation between engine and game, and demonstrates that our architecture is reusable. Overall, these ideas have come together to create a game that's both interactive and meaningful. Thank you. I'm Tanvi, and I'll be walking you through our live demo. So this is the start menu of NutriQuest. The game supports basic controls such as WASD to move the player, and enter to confirm selections, and we use escape to pause the game. So I'll begin the game now, so I'm pressing enter. This is level 1, so the basic objective is just to collect healthy food items to increase the score, and also avoid unhealthy food items at the same time. So the player is controlled using the keyboard input, and movement is handled by the engine's movement manager using delta time to ensure smooth and consistent motion. So when I collect a healthy food item, my score increases. When I collide with an unhealthy food, my health point decreases, and a quiz is triggered. The player selects an answer, and the result directly affects the state of the game. So the correct answer supports progress, while incorrect answer reduces the health points. So the food items move differently depending on their type. Healthy food moves more gently, while unhealthy foods move more aggressively. This is implemented using strategy pattern, allowing movement behavior to be changed without modifying the core entity. The game also includes a power-up system with 3 types: freeze, shield, and double points. Each power-up is implemented using a common interface, allowing flexible and modular behavior. When activated, the effect is shown on the HUD and affect the gameplay for limited duration. As the player progresses, the game transitions to the next level. The game can also be paused and resumed by pressing the escape button. And this is our last level. Overall, NutriQuest demonstrates a clear separation between the reusable engine and the game layer. The engine handles core systems such as input, movement, collision, and scene management, while the game layer implements features such as food logic, quizzes, and power-ups. So this results in a modular, extendable, and maintainable system. Thank you.